Hi friends, welcome to my channel. This is part 2 of solved examples on diversion head work on seepage theories, concrete glashes where floor thickness and corrected pressures at key points will be seen, and we will have more examples on this one. Okay, so let's see this example first. For the section of hydraulic structure founded on sand shown below, determine the average hydraulic gradient. So you have sheet pile and also two sheet piles and one just weir with 4 meter width and with a dimension given. So you are going to calculate the average hydraulic gradient, and also you have uplift pressure at points A, B, C of the downstream floor, the thickness of floor at points A, B, C using Bligh's theory, and take specific gravity of floor material as 2.24. So this is just to calculate hydraulic gradient and uplift pressure for horizontal floor. So we are given horizontal floor. So let's see the solution step by step. So the first step is determine the creep length. So the creep length, which is twice times d1, you have 2 times d1, and again plus b plus 2d2, and then you get 50 meter. And then you have average hydraulic gradient. So first you have to calculate head loss. Head loss will be computed first, this head loss, which is given by upstream water level minus downstream water level. So H1 minus H2, which is 4 meter. So you have this is head loss. Then next step will be, so you have again just hydraulic gradient, which is head loss divided by total creep length. So you get this value, which is important. So this is hydraulic gradient, and then next to this one, so you will have again, so considering a horizontal floor of length L subject to seepage head, the residual head at any point P is given by this equation. At any point P will be computed using this equation. So once you have this equation, then let's compute. The vertical intercept of hydraulic grade line is measured above the top of the surface of the floor. So let's see now. So the first step is you have to see uplift pressure points at A, B, C. So according to the above formulas, so you are going to compute now, which is H. H is just the residual uplift head, which is seepage head minus head loss. Then head loss is hydraulic gradient times creep length. Then you have this at point A. At this point, you have to compute, which is H, which is this one, H minus head loss at point A. So you have hydraulic head minus hydraulic gradient times the length of at A, up to A. So you have 4 meter total, just H, total H already given. Then you can find just 4 meter minus 1 over 12.5, which is hydraulic gradient times 80 up to, this is 4. So you have just it is going like this. So 4 times 4, 4 times 2, 8 plus 10 up to this point. Then you have 80. Clear? Then you get this is HA, hydraulic or the ordinate of hydraulic grade line, and at point B, which is this one, H minus HLB, which is this. Then 4 minus 1 over 12.5 times 28. 28 means you will add 10 meter again up to this point, up to point B. Then you get 1.76 meter. Then at point C, you have HC, which is H, you have H minus HL up to C. Then you get hydraulic head, which is H, which is the total seepage, total uplift pressure head. Then you have hydraulic gradient times LC. So you just up to C point, you get this dimension, which is 38. Then you get this value. Then check uplift pressure head at point C. So at point C, you can check now 1 over hydraulic gradient times just the head loss. The head loss across a cutoff will be 2 times 6. You have twice times 6, then you get 0.96 since it is equal with this one. So it is okay. So next step is determine the thickness of floor at point A, B, C using this equation. So for design purpose, we are going to use this equation with factor of safety 4 over 3. Then H is hydraulic head at each point, then you will substitute. So the thickness of A, B, and C can be determined as this is the equation. You simply substitute HA, you have hydraulic head or the ordinate of hydraulic head at point A, then G minus 1, so you get this thickness. And at point B, you get this value, 1.89, and at point C, you just you substitute HC, then you get this result. So I think this is important. Then next step, piping failure will not occur. Piping failure will not occur if the hydraulic gradient is equal to or less than a safe value. Equal to or less than a safe value. So for a safe design, you have to check this one. The hydraulic gradient, which is this one, which is head loss divided by LC, which is the hydraulic gradient, should be less than or equal to 1 over C, or creep coefficient. So if you crisscross this one, so you are going to find this is the safe creep length, the seeping of water under the base of the floor of the weir. So where C is Bligh's creep coefficient or percolation coefficient. So you can see just for light sand and mud, you have creep coefficient, then safe hydraulic gradient will be 1 over C, and fine marcaceous sand, you have this. So these are the safe hydraulic gradient. So we will check with this one. Okay, so ordinate of hydraulic grade line, ordinates are shown as below. So you can see hydraulic grade line, which is the ordinate, you can draw just subsurface hydraulic grade line. For each cutoff, you can have like this. So up to here, head loss across this cutoff will be the head loss divided by the length times 2 times D1, and this is also 2 times D2. This is again 2 times D3. So which is just critical hit, which is at point C, you can find just safe hydraulic gradient. Once you compute, then H upstream, you have H upstream minus head loss divided by creep length times 2D1. Then finally, you can have just, you can substitute in place of H upstream head loss. If no tailwater is if no tailwater, you can just have this one. For no tailwater, H2 equal to 0, then you will have this equation, general equation. You can compute H, which is ordinate of hydraulic grade line at any point C. You can find length up to C, and then 2 times D1. If you have D1, so you can find this is the ordinate of hydraulic grade line, HC. This is HC. Okay, example 3.4, Bligh's and Lane's theory. For the section of hydraulic structure at static condition shown below, determine the hydraulic gradient and the head at point C using Bligh's and Lane's theories, and check the safety against piping and uplift. The water percolates at A here and exits at point D. Take G, this one. So first you have to find the head loss. So H1 minus H2 will be 6 meters. Then you have 3 cutoffs. You have cutoff 1, cutoff 2, and cutoff 3 with this dimension, 15 meter up to point C, 10 meter, and 20 meter. Then let us calculate using Bligh's creep theory. Total creep length will be 2 times 2D1, 2 plus 2 times D1, because you have depths twice, and then 10 plus 2 times D2 plus 20 plus 2 times D3 plus 2, according to the drawing. If you see this drawing, so you have just the seeping of water is going like this. You have to D1, then you have 10 meter, then again 2 times D2, then it will go like this, 20 meter, which is this dimension from here up to here. Then you have 2 times D3, then this is the total creep length according to Bligh's theory. So you get 64 meter. This is total creep length, and then hydraulic gradient is just HL divided by LC. Then you get this is hydraulic gradient. Hydraulic gradient. So once you compute the hydraulic gradient, then according to Bligh's table, the structure is safe on gravel and sand from table. We will check this value in the table of Bligh's creep coefficient table, but not on coarse sand and fine sand. So remember, this is just for safe hydraulic gradient. You will have head loss divided by length of creep must be less than or equal to 1 over creep coefficient. So creep length up to point C, you have to check up to point C, 2 plus 2 times 5 plus 15 plus 2 times 3 will be 33 meter according to Bligh's theory. Then the residual uplift head at C will be, this is a safe hydraulic gradient. So this is just according to Bligh's creep coefficient table. You have safe hydraulic gradient and creep coefficient for each type of soil below the structure. So this is the structure. Now you can see just creep lengths up to point C, which is up to this point. You have two thickness of floor. Then 2 times 5 it will go. Then you have 10 meter. Then 15 meter. This is from here up to here, 15 meter plus 2 times 3, 33. Then the residual head will be like this. You can compute head loss. You have already 1 minus creep coefficient and also length of creep and the length of CPH up to point C. You substitute, then you get 2.9. Then thickness at point C will be, you substitute, this is HC or D you have, which is hydraulic head at point C, 2.9 divided by G minus 1, 2.34, which is greater than 2 meter, which is unsafe for uplift. So for uplift, we will check the thickness of the floor, and for piping, we will check with hydraulic gradient, safe hydraulic gradient. Okay, using lens weighted creep theory, you have this one. Sum of all horizontal contacts divided by 3 plus vertical contacts. So let's see. Weighted creep, you have 2 thickness of floor, then 2 times 5, which is D1, then plus 2 times D2. These are vertical contacts, then 2 times 7, then plus 2, then you have 1/3 of 10 plus 12. These are just sum of horizontal contacts. Then you get 44 meter. This is the total weighted creep lengths. But creep lengths up to point C will be 2 thickness of floor, 2 times 5 depth of cutoff, plus 2 times 3. This is again depth of cutoff, plus 15 over 3 up to C. You have 23. Then hydraulic total head loss divided by the length of the creep up to C. Then you have 1.733. According to length table, the structure is safe on fine sand, but not on very fine. So you simply check the table. Then finally, the residual uplift pressure head at point C will be this one. Just you will have up to C, you have already computed 23 over total, then 2.86. Then you can find the thickness of floor at point C, which is ordinate of hydraulic gradient up to C, hydraulic head. Then you have 2.86 divided by G minus 1, 2.3, then greater than 2 meters. So this is unsafe for uplift because we are given 2 meters. So if you are given thickness, you can check this one. This is for checking purpose. But for design purpose, you should multiply by 4/3. So this is for checking purpose. Then you can see just you can check the hydraulic gradient here. The hydraulic gradient, which is 1/7.33. So it is safe on fine sand. You can see this is the fine sand, so it will be 1/7 around. So it will be safe. Okay, so as exercise, you can check this one, Bligh's and Lane's theory. Assume there is a weir founded on previous foundation with floor thickness of 0.5 meter. All along cross section, you have seepage head, 6 meter upstream cutoff depths, 6 meter downstream cutoff depths, 8 meter, middle cutoff depths, 3 meter, floor thickness, 50 centimeter, upstream impervious floor up to the middle of the wall. You have downstream impervious floor from middle of wall, 20 meter, distance from the middle to the heel of the weir, 5 meter. So you are going to determine the hydraulic gradient of seepage using Bligh's theory and Lane's theory and calculate the uplift pressure at the heel of the wall using both theories and check the safety against piping and uplift. So you have this one. So you should change this statement into drawing first. This is the overall drawing because you have seepage head already given 6 meter, no tailwater. If seepage head is given, so you don't have any tailwater depth, so you have 6 meter here. Then upstream cutoff depths, you have upstream cutoff depths which is 60 meter, and again downstream cutoff depths 8 meter you have, and middle cutoff 3 meter. Once you put this one, then floor thickness again 50 centimeter, so you have to put 0.5 meter. Then upstream impervious floor up to the middle wall. This is the middle wall, 10 meter only given. Then distance to the downstream impervious floor from the middle of the wall is 20 meter. From the middle, this is the middle, this is the last for the downstream. So you have 20 meter, and distance from the middle to the heel of the weir, which is this one. This is the heel of the weir, which is at this point. Then you have 5 meter. So you are going to calculate the uplift pressure at the heel of the wall using both theories. So you are going to calculate the seepage up to point X. Then you can find the total creep length up to point X, then hydraulic head. Then finally, you can arrive at the solution. Let us see length of creep up to C. Length of creep up to total Bligh's creep theory. 2 times 6 you have, this is 2 times 6 here, 2 times 6, then it will go again 2 times 3 you have, then 2 times 8, these are the cutoff depths, you will multiply both sides, then plus 10 meter, you go 10 meter, then 20 meter, you go 20 meter, then plus 2 times 0.5 because you will include this thickness of floor because water is entering through this side and exits through this side. So this is 65 meter total creep length according to Bligh's theory. According to Lane's theory, you will have 1/3 of horizontal contacts. Clear? 1/3 of horizontal contact you have here and here. So this is 45 meters. The rest is the same. Then Bligh's gradient, which is just according to Bligh's hydraulic gradient, you have total seepage head divided by creep lengths, you get 1/10.8, safe for gravel and sand. And Lane's gradient, again, 1/7.5, safe for fine sand. I will display the table. And Bligh's length of creep up to the heel of the wall, up to X, up to this point, you have 2 times 6 plus 10 plus 2 times 3, then plus 5 meter, then plus 0.5, then 33.5 meter. 33.5 meter. So this is, I think, Bligh's theory up to this point. And Lane's equivalent length of creep you have up to the heel of the wall. you have 2 times 6 plus 0.5, which is this one, plus 2 times 3, then 1/3 of 10 plus 5. I think you can ignore this thickness because at the base, at this point, we are just, so you can take 33 meter, 33 meter, 33 meter. Then let's compute now. So according to Bligh's theory, you will have you can interpolate the hydraulic head. The hydraulic head is like this. As the 2 points, just you have here at this point already, you can find at this point, then at x point will be at this point, at x. So you have seepage head, already you have here 6 hydraulic gradient, then you have total creep length 65 from here up to here, then 33.5, which is up to this point, which is the length of the creep up to x. Then you can interpolate now. What will be the head? It will be around 2.88 something if you take 33.0. Then according to Lane's theory, you have 2.88. You simply substitute 45 here by interpolation. By interpolation, what will be h here? So both theory, Bligh's theory is more conservative because it is larger than Lane's theory. So I think part C left as exercise for students. So for checking purpose, don't forget to use this equation for thickness. But for design purpose, if thickness is not given, you can just design using this one. So I hope this is enough for part 1 session. I will proceed in the next slide, which is for concrete glacis weir or slope weir. So this is, I think, a nice example. I do hope you like the video. If you have any question or comment regarding this tutorial, please forward through comment suggestion box. I will reply on it. Okay. ጥያቄ ካላችሁ በኮመንት suggestion box ላኩልኝ. Any ambiguity. If you have any question or doubt regarding this tutorial, please write down in the comment section below. I will reply on it. Thanks again.